Hello, quantum explorers.
And the best time travelers of the universe.
Cool, time travelers. And I see you have a very cool t-shirt today. We will indeed be talking about time travel. Welcome back to the Quantum Kid. I am Katya Moskowicz, science communicator and theoretical physicist.
Hi, I'm Kai, the Quantum Kid, and I really like the movie Back to the Future, where the kid Marty travels back in time and then almost gets erased from existence.
Yeah, we will be talking about that today. And we have really great guests joining us to talk about quantum and time travel, to be exact. Who is joining us today, Kai?
Scott.
Exactly. Scott Aaronson, one of the world's leading experts in quantum computing, and Schlumberger Centennial Chair of Computer Science at the University of Texas at Austin, and actually also director of its Quantum Information Center. Welcome, Scott. Really great to have you here with us.
Thanks so much. It's great to be here. It's great to meet you, Katya and Kai. And Kai, I love your shirt. You know, I should say I have an 8-year-old son who also loves Back to the Future. We saw it live on Broadway, and he just couldn't stop talking about it for weeks, especially the way that Marty was able to confront, see his own father as a teenager, and he had to teach his own father to be brave. He loved that. He couldn't get over it.
What did you find interesting about Back to the Future? You had some questions.
Is time travel even possible?
Okay, well, there's a saying that we're all time travelers, right? We're all traveling through time at a rate of 1 second per second. Okay, but we're traveling forward, of course. Now, Einstein's theory of relativity tells us that we could travel forward through time at different rates. Okay, if we were traveling at close to the speed of light. If you got onto a spaceship and went at nearly the speed of light and then you came back to Earth, then people on Earth could have aged 40 years while you had only aged a month. Okay, so that's also possible. But now what most people mean when they're asking whether time travel is real is time travel to the past. And that's also called closed timelike curves. See, I wrote it on my board behind me. Okay, a closed timelike curve would mean that as time goes forward, you actually go backward to your own past. And you, just like in the Back to the Future movie. No one knows whether that is possible, because in order to really answer that, we would need a quantum theory of gravity, a theory that combines quantum mechanics and general relativity. And we don't really have that describes our world. We know that a lot of things that we think are true about physics would break if there was time travel to the past. But, we don't know for sure that it isn't. And even if it's not, it's still very interesting to study what would change about physics if it were possible.
What if it were possible indeed? I went to Chile to the Atacama Desert to find out. And this is Alma, another observatory. Let's go explore.
Hello.
This is Daniel. He'll be our guide for today. ALMA stands for the Atacama Large Millimeter Submillimeter Array. It is a radio observatory. It consists of 66 antennas on top of a mountain at 5,000 meters altitude. These antennas study space and also study black holes. Astronomers here use radio waves, not visible light, so they don't observe black holes directly but study gas and dust near them. Black holes form when a massive star dies in a supernova explosion, and they also exist in the centers of galaxies. Our Milky Way has one as well. It's super duper massive. In 2019, astronomers released the first image of a black hole in the center of a nearby galaxy called M87, or rather, its shadow. Did ALMA help with taking an image of a black hole?
To get an image like that, we need a huge telescope, really, really big in size. How big? Pretty much as the size of the Earth. The problem is we can construct that big machine, That's why we use different technologies that allow us to connect observatories across the planet in the way we transform Earth into a telescope once a year. April, by the way. That is the very first image of black hole ever taken. Well, it's not exactly the black hole, it's more like what's happening around it. In the center of that is where the black hole is located. So the image is regarded to the accretion disk. And the thing is how the image looks like. It's showing exactly in the way we expect light should behave around a black hole. But yeah, ALMA was part of it, and actually ALMA for the sensitivity. The project got a beautiful name. It is known as EHT, that stands for Event Horizon Telescope.
Since then, the EHT also took a picture of a supermassive black hole in the center of our own galaxy. Its name is Sagittarius A star. So, what if I were to jump into a black hole? Well, it's impossible. As you cross the event horizon of a black hole, you can no longer escape. But even if I would get close to a black hole, time would begin to stretch because of time dilation that Einstein's general relativity describes. For me, time would run as normal, but what I would experience as minutes for people outside would be years and years. So when I would get back to Earth, my family and friends will be years and years older. So I'll travel into the future.
So, about the closed timelike curves, maybe we could get a little bit more in depth on that, and
Sure.
you could just elaborate on how science actually connects to what we see in these movies in Back to the Future. And also you mentioned traveling through black holes, for example. That's what we saw in Interstellar, right? So what's real, what's not?
What a lot of movies feature, including Interstellar, is a wormhole, right, that would connect two distant regions of space and let you travel faster than the speed of light. Now, another very important thing that we learned from Einstein's theory of relativity is that having a wormhole is basically equivalent to having a closed timelike curve. They're basically the same thing. So in other words, if you could travel faster than the speed of light, then you could also travel backwards in time and vice versa. And the reason for that is that, Einstein taught us how space and time are connected to each other. For example, if you had a wormhole between 2 points in space and you just took one end of the wormhole and you put it into a spaceship and then that spaceship flew at nearly the speed of light, well, then when it comes back, now that wormhole is connecting two different points in time, right? Because time moved slower for the spaceship. So when we ask if closed timelike curves are possible in Einstein's general relativity, this is basically asking, could we have a stable wormhole? Could we have a wormhole that stuff can actually pass through, information or matter? Physicists like Kip Thorne studied that question. Actually, one reason why they studied it was that Carl Sagan, the astronomer, was writing a novel called Contact, that involves wormholes. And he asked them for the purpose of his novel about what does general relativity say about this. And that's why they investigated it. Okay. But what they discovered was that you could maintain a stable wormhole if you had matter of negative energy density. But we've never seen that in our universe. All the matter and energy that we've seen has positive mass, positive energy. But if you could violate that, then that could give you a way to keep a wormhole open. We don't know if stable wormholes can exist, but it's connected to a lot of other very mysterious things in physics. What we do know is that if wormholes existed, if closed timelike curves existed, then they would lead to paradoxes that physics would then need some way to solve. The most famous one is called the grandfather paradox. Kai, have you heard of the grandfather paradox? It's a little bit gruesome the way people usually talk about it, but I think you're old enough. So the way that the story usually goes is that someone goes back in time, like back to their grandparents' time, and then they kill their own grandfather. And then because they killed their own grandfather, then they can never be born. They've changed the whole history of the world to a world where they were never born. But then if they were never born, then that means that no one went back in time to kill their grandfather, right? But then that means that they are born. Okay, so that means that they do kill their grandfather, and so on. And I was like, what?
So it's
Okay.
similar to what happened to Marty, right? In the
Hmm.
movie and in the musical.
Oh, yeah, okay. Because he went like back in time at the time of where he was not born yet, and then he was disappearing from existence. Um, because his father and his mother almost didn't get remarried. I also saw with Interstellar that
Mm.
if you're in a normal world, time is infinite and space is finite. And then it said that in a black hole, space is infinite and time is finite.
I think I know what they may have meant by that, but I should say that no one actually knows whether space is infinite in our universe. And nor do we know whether time goes on infinitely. Time seems to have had a beginning at the Big Bang. We don't know if it has an end. These are really big questions. Now, the grandfather paradox is a really huge problem for any theory that would allow closed time-like curves to exist. And so usually when you watch movies, they just have some way that they make up, as they go along to deal with it. I remember in the Back to the Future movie, they had this whole thing where like if someone no longer exists, then they fade out of photos. That one really didn't make sense to me. Another thing that they often do is they say like when people go back in time to maybe the time of the dinosaurs or something, and they say you have to be very careful not to change anything, not to move any rock or something, because if you do, then that could change the whole future and that would mean you would never exist. Now, I think the truth is, as soon as you appeared there, it's already over. As soon as you went back to the past at all, disturbing the air, you're even just by being there, you're slightly changing things, and that's going to cause a ripple effect that's going to eventually change the weather, and that's going to change the whole history of the world, right? And probably cause different people to be born instead of you. Okay. So but then that brings us back to the paradox. If you go back in time and you change the future so that it's no longer the future, well, then you didn't go back in time, right? So how do we deal with that?
How do we deal with
Yeah,
that?
so there have been proposals over the years for how you could try to make sense of a closed time-like curve. What they generally say is that somehow the laws of physics have to make everything consistent. Some stories deal with that by saying like if you try to shoot your grandfather before you were born, you'll always find that just the gun mysteriously jams, and then it will turn out that like in the original history of you, someone had tried to kill your grandfather but failed, and that person was actually you. But then that leads to a second problem, which is how does nature actually make everything be consistent? So let me tell you about a different paradox of time travel, okay, different from the grandfather paradox. This one is called the Shakespeare paradox. Okay, so this one says, what if you went back in time to the time of William Shakespeare, and you say, I actually have your collected works. I have all your plays. I have all the plays that you're going to write. And Shakespeare takes that book and he says, I thank you. You just saved me a lot of work. Now I don't have to write them anymore. Right? Now I just have them right here. And so then Shakespeare just copies from the book that you gave him, and everyone has the plays. Now notice that unlike with the grandfather paradox, here nothing is inconsistent. You went back in time, gave Shakespeare the plays, therefore Shakespeare has the plays, therefore you have the plays. The only paradox is that somehow Shakespeare's plays, like Romeo and Juliet, somehow came into existence without anyone ever doing the work of writing them. So how did that happen? There are also proposals for how if closed time-like curves existed, then computers could solve extremely hard problems. And they're very similar to that Shakespeare paradox. Like you can imagine a situation where, let's say, you're trying to break a cryptographic code. And there's this enormous number of keys that, to try, more than you could try out in the whole lifetime of the universe. This is how modern cryptographic codes usually work. They have this enormous number of keys, and in theory, someone could break it if they guess the right one, but there's just too many to try. But now imagine that you had a closed timelike curve. And so then you could tell your computer, try a key, and if the key is correct, then just send it back in time to the past. And so then it meets itself and it's, everything's consistent. But if that key is not correct, then replace it by a different key. Okay. And then send that one back to the past. Okay. So imagine that that's what you program the computer to do. And then we could say the only way for nature to make that computer do something consistent is for it to have a correct key. Because if it doesn't have a correct key, then it's going to receive something different than what it sent. So that's the basic way that closed timelike curves, if they existed, could make computers like super duper powerful, way more powerful than we think that even a quantum computer would be, right? Quantum computers are something that we're hoping to actually build, but those only give big speed ups for some very, very special problems. If we had a closed timelike curve computer, that would give a speed up for just about all the problems that we want to solve, involving breaking cryptographic codes or optimizing travel schedules and all kinds of things like that.
So if quantum computers could talk to their past selves, would they then become extremely powerful?
I wrote a paper with John Watrous in 2008 where we argued that the answer is yes. They would become way more powerful than we believe, an ordinary quantum computer would be. But what we even showed was that once you have a closed timelike curve, it doesn't even matter whether it's a classical computer or a quantum computer. Both of them would jump up to the same extreme level of power, which is something called p-space. It would be the ability to solve every problem that a conventional computer could solve using a reasonable amount of memory, but reusing that memory over and over and over for what might be an astronomical amount of time. So we said, if closed timelike curves existed, then this is the answer, and it's this p-space as to what problems you could solve, and it's way beyond what we believe that even a normal quantum computer could solve.
And what we were saying before about changing the past, for example, so if we are already disturbing everything just by going back, what about different timelines then? Would that be possible if a new timeline would just branch out and continue?
Yeah. So this is actually one of the main proposals. In fact, in order to write our papers about computer science and the presence of closed timelike curves, we needed a mathematical model of what a closed timelike curve even is or does. So in order to study these questions, we used a mathematical model of time travel that was proposed in 1991 by a physicist named David Deutsch. Now, David Deutsch is also famous for being one of the inventors of the idea of quantum computing. In 1991, David Deutsch argued that quantum mechanics could give us a way of dealing with the grandfather paradox, okay? And specifically, using this idea of multiple timelines. In quantum mechanics, before you make a measurement of something, it doesn't have a definite state. It's in what we call a superposition. You don't know where the object is. It might be here. It might be there. But you can't just use probabilities. You can't just say there's like a 30% chance that it's here, a 70% chance that it's there. That we do all the time in normal classical physics, just because we don't know everything. But in quantum mechanics, you have to assign these numbers called amplitudes. Amplitudes can be positive or negative. In fact, they can even involve the square root of -1. They can even involve imaginary numbers, okay? And if something can happen one way with a positive amplitude and another way with a negative amplitude, then the two possibilities can cancel each other out, which means that thing never happens at all. That's the crazy thing in quantum mechanics. And so now what David Deutsch said in 1991 was, okay, when we think about closed timelike curves, we have to remember that as far as we know, everything in our universe is ultimately quantum mechanical. And so you don't have to just definitely be alive or definitely be dead. There could be what we call a superposition of the two, right? Both possibilities could exist in parallel timelines. Each one can have what we call an amplitude. For example, in the grandfather paradox, The solution might just be that you are born or you are, not born with equal amplitudes. Okay, there's a superposition of the two, or you're born with probability 50%. You're not born with probability 50%. Now, if you're born, then you're going to go back in time and you're going to kill your own grandfather. If you're not born, you won't. But what does that mean? That means that you're born with 50% probability, just like we said at the beginning. So everything's consistent and there's no paradox. Okay, here, I drew a little picture of it here, right? There's two timelines where you kill your grandfather and where you don't. Hey, but each one feeds into the other one. So if you go back in time and you kill your grandfather, that creates the timeline where you're not born. But if you are not born and you don't kill your grandfather, that creates the timeline where you are born. So Deutsch's rule is that you specify, what the laws of physics do, or like what your computer does, for example, acting around this closed time-like curve. And the part with the closed time-like curve could also be interacting with the normal part of the universe, where time just flows forward in the normal way. But then in the part that has the closed time-like curve, nature is somehow forced to find a fixed point. A fixed point means a quantum state that is mapped to itself by whatever computation happens there. So, for example, with the grandfather paradox, the fixed point was that you're born with probability half and you're not born with probability half. And then Deutsch proved a simple theorem, which says that in any quantum system involving a finite number of bits, there will always be at least one fixed point. So then that is his proposed resolution of the grandfather paradox, that, if these fixed points always exist and nature always just somehow finds one of them. If there's more than one, then we don't know which one nature would pick. That's left undetermined here. Okay, which is a little bit weird, but at least these fixed points would always exist. Deutsch proved that.
Very cool.
So could I just take my homework, go back in time, give it to myself, and
Yep.
then myself would say, I done this homework, and then I go back to my time, and then I will get everything correct.
In a world that it was described by Deutsch's kind of closed time-like curve, yes, that is exactly what you could do. This would require that you're able to check your homework. So, you would need to do the action where you check your homework and make sure that it's correct. But if you can do that, if you know how to recognize a correct homework solution, then using the closed time-like curve, you could instantly create the correct solution.
Great. Well, we're nearly at the end of the episode now. Would you like to travel in time?
No.
All right. Well, then I have some good news for you, Kai, which is that most physicists would probably guess that none of this is possible. Okay. It's super fun to think about and to see how well our theories would extend to this. But the very fact that we get all these computational superpowers, some people would take as an additional argument for why closed time-like curves should not exist. But even if they can't exist, then proving why they can't exist is a task for the physics of the future.
Absolutely. All right. Well, thank you so much, Scott. I just want to thank also our audience for joining us today. I'm sure you learned quite a bit, as have we. And please do join us again next time on the Quantum Kit. And don't forget to subscribe to our channel and to like us, of course. And thank you again, Scott, for joining us.
Of
Goodbye.
course. Pleasure.
Bye.